Okay, I think we can start with the second talk. The second talk will be by Matthias Langer, who's coming from Vienna actually, and he's working on a project with microservice based based on microservice architecture, and he is also a contributor to the Scala IDE environment and ecosystem. He's working on a Scala refactoring library, and he will present a little bit more details about it. So Matthias, the audience is yours.
Thank you very much, Rafael. Yes, as already mentioned, today I want to tell you a bit about problems and perspective regarding the Scala refactoring library. Can you all hear me well? Is it loud enough even in the back? Great. So before I start, let me use this opportunity to actually thank my employee Iriam for supporting me to come to this conference. And of course, I also want to thank Virtual Lab for hosting this great conference. And last but not least, of course, all people from the Scala IDE team who have been working together during the last year. So in this talk, after a short introduction, I want to talk a little bit about the architecture and the problems that are related to the architecture of the refactoring library. And in the end, I want to present some perspectives for the future of the refactoring library that might address the problems I'm going to explain in this presentation. So, well, let's start with a brief overview of the Scala refactoring library. So the Scala refactoring library was created by Mirko Stocker in the year 2009 as part of his master thesis. And it's an IDE-independent refactoring library that is currently used by both Eclipse Scala IDE and Enzyme. And it supports both Scala 2.10 and Scala 2.11 and has really, in theory at least, lots of features. But in practice, unfortunately, as you might have already found out, it's quite buggy. And so what's my role in all this? I started contributing to Scala IDE at the end of 2014. And since I'm also using Scala IDE at work, and I like to refactor my code a lot, I soon became very annoyed by various refactoring bugs in the refactoring library. And so I decided to try to fix them, and that's basically what I've been doing over the last year. I've just been fixing lots of bugs, mostly related to move class, rename, and organize imports. So really only related to the most basic refactorings. And but since I'm only doing this in my free time, my resources are rather limited, and there are still many bugs left. So before I continue, I want to insert some sort of disclaimer. What I'm going to say here is, of course, my personal opinion, and I won't also tell you how great things are. Because, as I already pointed out, unfortunately, the refactoring library is quite buggy. But the good news is that I learned a lot, not only by fixing bugs in the refactoring library, but also by preparing this presentation, because preparing this presentation really forced me to see things in perspective. And I want to share the conclusions that I came up with you today. So let's take a closer look at the architecture of the refactoring library. The Scala refactoring library works with the abstract syntax trees it gets from the Scala presentation compiler. And for those of you who are not familiar with abstract syntax trees, I have a small example here. So that you can familiarize yourself with them a bit. On the top of the slide, you see a very basic identity function that operates on the integers. And down here below, you see the little simplified version, actually, of the related abstract syntax tree as it is generated by the Scala compiler. And maybe I should also mention, for those of you who are not so much into compiler internals, that abstract syntax trees are generally generally tree-based data structures that are used by compilers to represent source code and programs. And so in this example, the function definition here is represented by this def node at the very root of the tree. And then you can see that the term name is encoded in this term name node. You can see the parameter x being encoded in this val-def node that has its own children. And last but not least, the trivial body of the method is encoded in this ident node. Yeah, actually you can, if you're curious about those trees, you can print them out very easily using the Scala compiler API. So can you actually read the source code? Oh, okay. So maybe, I'm not sure if I can make this bigger. Just give me a second. Well, maybe that's really.
I can tell you command comma.
Yeah, command.
Command comma.
Yeah.
A type font in the search box.
Yeah. Where is font?
Not just type font is in the filter. Yeah, font. The first one. Click there.
Appearance. Yes.
The next one. The bold one.
Yes.
Yeah. And open whatever Java.
Yeah. Okay.
Java editor. Yeah, that.
And now you
Edit.
okay.
And now go there.
14.
Okay, then you have to close the window.
Yeah. Okay. All right.
Click apply.
Let's see if this helps. Yeah. Thank you very much. Yeah. Is it better now, or should I make it even bigger? Bigger. All right. Maybe I'll do it without help now. Let's see. So let's just try 24. So let's see. Yeah, better? Okay. So yeah, here in this example, yeah, you can see how to actually print these trees. Here we just load a piece of very trivial Scala source code that looks like this, and we then convert it to a string, and then we use a toolbox from the Scala compiler API to parse and type check this piece of source code, and then we just print out the AST with by using this strange method here called showRaw. I don't know why it's called like that. But if we do this, let's see what happens. Okay, now I have to modify another font. Okay. Yeah.
How about you copy paste the stuff there?
You mean into the? Yeah, it's a good idea. So let's do it like this. Yeah, so you see this is one huge string that you can really easily make any sense of. And because this, if you wanted to make sense out of this, you would now have to reformat it. And because I often was in the situation that I had to understand a specific tree. I wrote a small tool that does the formatting for you automatically, and that you might find handy if you also happen to work with abstract syntax trees or other expressions that involve a lot of parentheses and are quite long. So let me just make a quick modification to this. Okay. All right, so now I've just run the example again. Using this formatter call I've just inserted. And if we look at the resulting printout now, you can see that it's properly formatted. So now I think it's quite easy to see the structure of this tree, because yeah, on the very top we have this module definition that defines our trivial object. And then here we see actually a constructor that is not present in the original source, because this like constructor definition was already generated by the Scala compiler. And finally, this trivial method that we already saw in the example at the beginning is this part of the tree. So well, I hope that you now have all a rough understanding about what abstract syntax trees are. And I think you can also imagine that a tree for a like regular piece of Scala code is just a huge beast, because this is only a trivial class and it's already quite a tree. But if you imagine some real-world Scala code with several hundred lines, this is, yeah, you can imagine that this will be quite huge. So let's continue with the presentation. Having said that, the Scala refactoring library works with the abstract syntax trees it gets from the Scala compiler, to be more exact, from the typer. This nice graphic here, by the way, on the top of this slide has been taken from Mirko Stocker's master thesis that you can, in fact, download from the internet. It's available on ScalaRefactoring.org. And if you are interested in the details and architecture of the refactoring library, then this is a very useful information source. And I also want to thank, of course, Mirko Stocker for allowing me to use this graphic in my presentation. So, well, so let's continue with the architecture of the library. So after the abstract syntax trees are generated by the compiler, the refactoring library takes them over, first performing some analysis, and then the actual refactoring, like a rename operation, or I don't know, extract method, or switch the order of parameters, is performed in this transformation phase. And then after the transformation has been applied to the abstract syntax tree, code is generated from the transformed tree, so that in the end we can we can come up with changed sets that can be consumed by IDEs to actually perform the refactoring for the user, because the user is of course not interested in abstract syntax trees, but the user wants to see a modification of his source code that represents the actual refactoring. So this is like the overall design of the library, and I think it's a good design. There's nothing to say against it so far. So let's look, in the following I want to look at these phases, namely analysis, transformation, and code generation in more detail. So the first phase is the analysis phase, and the most important thing in the step in the analysis phase is probably index lookup, because if you, for example, do a rename refactoring, then it's very important that you are able to find at first for any given symbol the place where the symbol is declared, and then of course you also need to find all the yeah, then you need to find all, of course, also all references for a given symbol. So if you do a rename operation, you don't want to miss a reference to that symbol. Then what's also done during the analysis phase is name validation. Refactorings often introduce new names into the program, so you have to make sure that these names are valid. Scala identifiers actually, which is done by like this method here. And then of course you also have to make sure that the names you introduce don't collide with already existing identifiers in the program. So that's like modeled by this does name collide method definition here. And another thing that's also done during analysis that's not on this slide is compilation unit dependency analysis. That is for organized imports, for example. You need to find all external dependencies of a compilation unit so that you know, for example, which import statements are unneeded and which must stay if you do organized import refactoring. Well, so having said that, let's jump to the next phase. This is actually like the meat and potatoes of the refactoring library. It's the transformation phase. It's where the actual refactoring happens. And you can think of a transformation as a mapping from a tree, from like a node in an abstract syntax tree, to an option of a tree. And you can combine these transformations. There are like combinators in the refactoring library with the combinators and then and or else. And maybe it's just most instructive to look at the two examples I've written down here. So the first example, it's actually very useless transformation, but nonetheless, it's created from a partial function that matches only templates. Templates are a type of syntax tree node that is normally used as an implementation for classes and traits and objects. And the body of a template normally consists of all like top-level statement in that class or object, so mostly method definition and value definitions. And this simply transformation just reverses the statements in this body for all templates, and all other trees would be mapped to none by this transformation. And the next transformation here is actually inspired by the actual implementation of the rename refactoring. Let's forget this top down here for a second. So we have a transformation here that is the identity transformation for all tree nodes that are tied to the symbol we want to rename. And all other tree nodes that are not affected by our rename operations are mapped to none by this operation. And this operation then is combined with the actual renaming logic that happens in the rename single tree transformation. So now we have a transformation that renames all trees that should be renamed, but converts all other trees to none. And since we don't want to simply drop all other trees but keep them unmodified, this transformation is then combined via or else with the identity transformation, so that unrelated trees are not simply dropped but kept unmodified. And now I can maybe explain to you what this top-down means. So if we go back here and we look at this tree, if we want to perform a transformation on it, of course we could either go from the top to the bottom, starting with this dev node and then transforming the term name and the valdev and so on, or we could go in the other direction from the bottom to the top, and that's what this top-down here actually means. So Well, after the, yeah?
So why do you need, do you need to press something?
Hello, hello.
Okay, so why do we need or else identity there on the previous slide?
Yeah, you need it because this tied to renamed symbol transformation that is not written down here on the slide converts all trees that are not tied to the renamed symbol to none, because the transformation is modeled as a mapping from tree to option tree.
Okay.
Are there any other questions maybe? So if something is unclear, just step in and ask me. All right. Well, so then the next, or the final phase that is performed for the refactoring by the refactoring library is the actual change set generation. So now we have like modified our abstract syntax tree. We have applied a transformation to it that represents our refactoring, and now we have to generate source code from these transformed trees again. And so the first thing that happens is that the trees that have been modified, the refactoring library has to find the trees that have been modified by the transformation. This happens in this changed tree detection phase. Because grossly simplified, the method that like prints out the trees in the refactoring library looks like this definition here. So if a tree has been modified, the source code is regenerated, and if the tree has not been modified, the original source code is just kept as it is. And well, the end product we are after, that's what later IDEs can consume to perform the refactoring for the user, is a list of text changes, where a text change is simply a source file with a range in that file and some text that should be inserted there in order to replace the old text that has been there before. So, well, as I already said, actually the really complicated part is this tree printing, as it is called in the refactoring library, this regeneration of the source code from the abstract syntax trees. And in the following, I want to outline why this step is so complicated. So the first thing that complicates matters for the refactoring library is that these abstract syntax trees contain absolutely no layout information. So if you look at these three methods here, then they all have the same abstract syntax trees. And of course, they are semantically equivalent. So this is perfectly fine for a compiler. But of course, for a refactoring library, this is problematic because refactoring is expected to keep the formatting from the user and not to mess around with it. But what's even worse is that the ASTs from the compiler are already desugared. What does this mean? So most of you might know that for comprehensions in Scala are just syntactic sugar for map, flat map, and with filter. And unfortunately, at the moment that the refactoring library gets the abstract syntax trees from the compiler, this transformation of for comprehensions into combinations of map, flat map, and with filter has already happened. So if you just look at the abstract syntax trees, there is not really a difference between these two method definitions. And that's of course also a problem because nobody wants a refactoring library to like convert for comprehensions into combinations of map, flat map, and with filter, or the other way around. Basically, the same applies for placeholder syntax. So if you look at these two method definitions, from a standpoint of the abstract syntax trees, they are basically identical because the compiler usually then introduces these syntactic variables with dollars in them. So that just looking at the abstract syntax tree, this method actually looks like this here. And the same applies to default arguments and named arguments, because there it might even get worse. If we look at this very simple function here that just calls g with named parameters using the default value for a, the abstract syntax tree that we actually get is this one here, which is of course fine for a compiler because that's the code that should be generated in the end. But for a refactoring library, this is very problematic, and this is actually the reason why up to this day the refactoring library doesn't properly support named arguments. So if you perform any rename operations and you are using named arguments, it will usually break your code because it can't deal with this discrepancy. So how are trees actually printed by the refactoring library? Well, since the ASDs, as I've lined out, doesn't contain the information necessary to print the trees, the refactoring library has no other option than to look back into the original source code and reparse parts of this source code using various hacks with regular expressions or handwritten parsers. In some cases, the implementation also depends on the implementation of the refactoring library is also very closely coupled to the implementation of the compiler. And this tree printing phase, so the last phase in this in the architecture of the refactoring library, is actually the most complex and buggy part of the refactoring library. And if you want to see what I'm talking about, you can just open one of the, you can just look at this one of these classes. We're using printer layout helper pimp trees that are mostly concerned with tree printing. So now you might of course ask, why doesn't the refactoring library use its own abstract syntax trees? And well, in fact, this has been tried, I think, in the beginning, but it turned out to be too complicated because writing a Scala parser and typer is really a major effort and not something you do on a weekend. And the point is you really need a typer to do proper refactorings, or at least a namer, because you need to resolve symbols. So just a simple parser is not enough. Yes?
So I would like to 1, 2, 3. Okay, I would like to comment on something. So just a namer would not be enough because in order to resolve references, you actually need to type check stuff. Because imagine if you write something like val x equals invocation of a function, and then you say import x dot underscore. So in order to see which names you bring into scope, you need to type check things. So that's very, very unfortunate. But well, this is how Scala is.
Yeah. Also, of course, for organized imports, you also need to type check because you also need to know which implicits are used in the code, and you can't see them without doing type checking, of course. Back then it was decided that implementing this from scratch was just too much work, and so it was attempted to do this with the abstract syntax trees from the Scala compiler. And with the results you can see now. I think the guys from IntelliJ, they implemented this all on their own, and I think this was the right decision. Well, actually, I'm coming to the end of my presentation. So now that I hope that you now have an understanding about the deeper architectural problems of the refactoring library. So my main conclusion that I came up with actually while preparing this talk is that refactorings based on the abstract syntax trees from the Scala compiler are very hard to get right, or even impossible to get right. And I think we should really try to move away from them Unfortunately, these abstract syntax trees from the Scala compiler are very closely coupled to the library. So moving the library to a new abstract syntax tree implementation means rewriting it from scratch. Since I'm only doing this in my free time, it's not realistic that I do this alone, so we would really need to have a team effort. But on the plus side, I think that the clean implementation would also attract more contributors. And then there's also Scala Meta. I'm very excited about it because, at least from what I know about it, it looks exactly like what the refactoring library could need, because it contains abstract syntax trees with all layout informations and without any desugarings. So I'm really excited about Eugene's talk just afterwards. So there are also some short-term improvements I would like to suggest that we should do. For example, I would really like to throw Scala IDE currently supports lots of refactorings in the context menu, and I think they're almost all completely unmaintained. And I think we should really just remove them and only keep rename, move class, and organize imports in there, because even these refactorings are buggy enough, but the other ones are, I guess, just not usable. And yeah, we could also overwork the README on GitHub to attract more contributors. But what we really should do is actually think about moving the library maybe to Scala Meta. I think this would be the best way to improve it in the long run. Yeah. So that's basically all I wanted to tell you. Are there any questions, remarks? I really would like to have maybe it would also be great if we had some kind of discussion. So if anyone disagrees or thinks otherwise, it's also fine. I would like to hear it.
About the strip printing, do you consider using positions from the AST? Positions, I mean.
Yeah, we actually use positions from the abstract syntax trees. And yeah, the library uses these positions then to look into the original source code and yeah, to find out what's going on there, to extract layout elements that are missing from the tree, or like find out if this is actually a for comprehension or really a combination of map, flat map, and so on. Yeah.
Did you thought about just rewriting the parser and reuse the type checker from the compiler?
Yes, actually that would also be an option, to just maybe use the parser from Scala Meta and then somehow use the abstract syntax trees from the compiler and like use them to add information to the trees from Scala Meta. But I think the time would be better invested if we get this right in Scala Meta from the start, instead of like doing it on our own.
So I just want to comment a little bit on the previous question. This thing that you brought up, it's exactly how Scala Meta is designed, and in just half an hour you'll see a bit more how it works.
Yeah. Yeah, all right. Thank you very much.
Yes, thank you. Thank you, Matthias. I took out the microphone from your hand, just, but no worries. I was not anything wrong. So if you have still any questions, so please grab Matthias on the around here. So hopefully we will get some feedback from you also regarding the refactorings and the refactoring of the code that you probably try or use on a daily basis. So it would be very useful. Okay, so if there isn't any more questions, we can thank Matthias and we can meet in 20 past 11, I think. 20 past 11 starts the next talk about the Scala meta by Eugene. So, okay. That's how it is.